about prime ideals, maximal ideals and their relations, and some few questions of CSIR net, NBSM and any competitive exam. Today at first I have thought I will review this relation again because these relations are more important for any competitive exam. The first theorem is, if R is a commutative ring with unity, then each maximal ideal be prime ideal. Other theorem is, let R be a commutative PID with identity, then every non-zero ideal P, which is proper ideal, is prime if and only if it is maximal. That means, if R is a commutative PID with identity, then maximal and prime ideal is if and only if condition. Maximal always imply prime and prime always imply maximal in this theorem. Are you getting the idea? This is true only when R is commutative PID with identity. But when the ring be finite, then all prime ideals always be maximal ideal. In a finite ring with unity, all prime ideals are maximal ideal. And this is possible when only ring the finite commutative ring with unity. And in my previous video, I did not prove this theorem. Today I will prove this theorem because for competitive exam, this type of theorem is very important. To prove this theorem, in a finite ring with unity all prime ideals are maximal ideals, to prove, at first I will prove, if R is a finite integral domain, that imply R is a field. Because if we can to prove this theorem, then this will be so easy to prove this theorem. At first I will prove this theorem. If R is a finite integral domain, that imply R is a field. At first consider U be non-zero element of the ring R. Now consider a mapping phi subscript U from R to R such that the defined mapping is phi of U are equal to U times R. At first I will prove this mapping is 1, 1. For to prove 1, 1, consider phi of U are equal to phi of US, and that imply obviously U are equal to US by the defined mapping. And from this line we can tell easily U times R minus S equal to 0. And since I have considered U be non-zero element of the ring, that means obviously U not equal to 0. That imply obviously R minus S equal to 0. And from this line we can tell R equal to S. That means from this condition, since R equal to S, I have got. That means this mapping is obviously 1, 1 mapping. Okay? And this mapping is obviously onto because here R is a finite commutative ring. So 1, 1 always imply onto. We all of us know this is. And since I have defined the mapping is like, so from this, and since R is a finite commutative ring with unity, therefore there exists obviously one V belongs to R such that UV equal to 1. This is actually the defined mapping phi of UV, and that implies U has a multiplicative inverse, and since here U be any arbitrary element of the ring R, obviously every element has a multiplicative inverse of the ring. That implies R is a field. Are you getting the idea? That means our proof has done. If R is a finite integral domain, that implies R is a field. Let's come back our original question. I will prove in a finite commutative ring, all prime ideal are maximal ideal. P subset of R is a prime ideal, then obviously R mod P is a finite integral domain. Since R mod P is a finite integral domain, that implies by this theorem mod P is a field. And since R mod P is a field, obviously all of us know the ideal P be maximal ideal. Are you getting the idea? Oh well. This theorem is very important for any competitive. Now I will see one question which had come CSIR NET June 2019 exam. The question is, let R be a commutative ring with unity, then which of the following statement is true? Option 1, if R has finitely many prime ideals, that implies R is a field. And option 2 indicate if R has finitely many ideals, then R is finite. Option 3 indicate if R is a PID, then every suffering of R with unity is a PID. And option 4 indicate if R is an integral domain which has a finitely many ideals, that implies R is a field. Are you getting the option? If you can to prove this option on self, then you will understand you have obtained a deep knowledge in ring theory. At first, see the first option. Here given R is a commutative ring with unity. And first option is if R is a finitely many prime ideals, that implies R is a field. For first option, if you consider the ring Q plus Q, then we all of us know this ring is not integral domain because this ring contains the zero divisor. Here, just recall, choose two elements which is non-zero, 1 0 and 0 1. This is non-zero element in the Q cross Q. But notice their product be 0. So, these rings contain zero divisor. So, this ring not integral domain. But notice the ideal of this ring. We all of us know, if we consider such type of ring F1 cross F2, where F1 and F2 be field, we all of us know ideal of any field is look like singleton set 0 and F itself. And if you consider such type of ring F1 and F2, where F1 and F2 be field, then ideal of this ring are look like F1 cross singleton set 0. This is one ideal. Similarly, I2 would be singleton set 0 cross F2. And other would be trivial ideal 0 cross 0 and whole ring itself. We all of us know these are four ideal of this ring. I have discussed this part elaborately in my earlier video. Are you getting why I have told you why my previous video is more important? If you don't see my earlier video, at first I will highly recommend you, please see my earlier video. Now let's come back this question. We all of us know the prime ideal of the field are only 0. This is the prime ideal of any field which is also maximal ideal. So for this ring, prime ideal would be these two ideal be prime and maximal ideal also. So ideal of this ring would be Q cross 0, 0 cross Q and 0 cross 0 and Q cross Q. And in this ideal, I1 and I2 be prime ideal. So this ring contain finitely many ideals. That means this ring contains finitely many prime ideals. But notice, since this ring is not integral domain, so obviously this ring not filled. That means option 1 is a wrong option. If R has finitely many prime ideals, then R is a field. And option 2, notice, if R is a finitely many ideas, then that implies R is finite. Notice, this ring contains finitely many ideals, but this ring is infinite. Is option 2 also wrong option. If R has a finitely many ideals, then R is a finite. This is wrong option. And option 3 indicate if R is a PID, then every subring of R with unity is a PID. Just think, this option is I have defined in my earlier video also. All of us know this result. If R is a field, that implies Rx is PID. And since Q is a field, that implies Qx is a PID. Qx means we all of us know set of all polynomial whose coefficient is rational number. And since Z is a subset of Q and obviously Z is a subring, that implies obviously Zx will be subring of Qx, and we all of us know Zx is not PID because the ideal generated by 2x not be generated by single element, so Zx is not PID. Therefore, third also wrong option. If R is a PID, then every subring of R with unity is a PID. This is also wrong option. And notice option 4. If R is an integral domain which has finitely many ideals, then R is a field. And obviously this option will be right option. But let's try to prove this option. Here R is an integral domain which has a finitely many ideals, then R is a field. Just recall the first theorem. This theorem is same like the first theorem. What this prove? Just construction will be different type. Just see the proof again. Here consider I tilde be the set of ideals of the ring. That implies I tilde is a finite, because since here given R is an integral domain which has a finitely many ideals. So the mapping here defined as like, consider A belongs to non-zero element of the ring R, and consider the mapping phi from I tilde to I tilde, and the mapping is look like phi of I equal to A times I. Are you getting the defined mapping? Let's recall, few minutes ago I have defined the mapping phi subscribe U which map from R to R such that phi subscribe U are equal to U times R. And here the mapping is this type, where I bar be the set of ideals of the ring. But here I have defined the mapping I tilde to I tilde, because here has told R is an integral domain which has a finitely many ideals, and I have considered I tilde be the set of ideals of the ring which is finite. Are you getting the difference? Well, now we have to prove as like before, phi is 1 1. For this, consider phi I equal to phi j. That implies by the defined mapping ai equal to aj. And from this line we can tell easily, for all I belongs to capital I, there exists j belongs to capital J such that ai equal to aj. And from this line it implies A times I minus j equal to 0. And since I have considered A be non-zero element of the ring, and since A not equal to 0, that means obviously I equal to j. And I equal to j means here I have considered for all I there it is j. That means from this line obviously this would be true. Capital I equal to capital J. That means our proof has done. Phi I equal to phi j imply I equal to j. That means this mapping is obviously 1 1. Okay? And since I tilde is finite, then 1 1 obviously imply on 2. And since 1 belongs to the ring R, so there exists some j belongs to capital J such that A times j equal to 1. Okay? And from this line it is, we can write it as this j is an inverse of non-zero element A. And since I have considered A is any arbitrary non-zero element, so obviously every element has an inverse of this ring. So that imply this ring R is a field. Are you getting the idea? Oh well. That means if R is an integral domain which has a finitely many ideals, then this ring obviously be field. Now I will say one important theorem. Let R be a commutative ring with unity in which every ideal is a prime ideal. Notice, in a commutative ring, every ideal be prime. Then that imply R is a field. Just think. The proof is look like AB equal to 0, then ideal generated by A times ideal generated by B equal to ideal generated by 0. And since ideal generated by 0 is a prime ideal, because here given every ideal be prime, therefore by the definition of prime ideal, this is either ideal generated by A equal to 0 or ideal generated by B equal to 0. Hence, AB equal to 0 imply, from this line we can write easily either A equal to 0 or B equal to 0. That means obviously from this line we, since imply either A equal to 0 or B equal to 0, that means obviously R is an integral domain. Okay? And if A belongs to R, then ideal generated by A times ideal generated by A obviously equal to ideal generated by A square. Since this is because R is a commutative ring, but here since every ideal be prime ideal, that means ideal generated by A square is prime. That means obviously ideal generated by A contain in ideal generated by A square. And from this expression, this is obviously A belongs to ideal generated by A square. Hence, there exists an element X belongs to R such that A equal to A square X. And from this line, this is obvious. A times 1 minus Ax equal to 0. And since A be non-zero element of the ring, so that means since A not equal to 0, that means obviously Ax equal to 1. And from this impression, this is imply A is invertible. Since I have considered it A be any arbitrary element of the ring. That means obviously the ring R is a field. Today I will stop here. I will highly recommend you. Please see today's video with pay attention. Because this type of example are very important for any competitive exam. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel. Thank you so much.